Okay, so I'm Mark Gusslin from Xilinx. We're going to talk about 400 gig E and how it's finally becoming real after many years of talking about it. I'd like to introduce my panelists. So I have Dave Ofelt from Juniper, a distinguished engineer, and a principal engineer, Brad Booth from Microsoft. So thank you very much for being on this panel. So the outline, we're going to talk about introduction and history of 400 gig E, just a very quick history. We've been working on it for about 4 years now. Seems like a long time, but it's finally here. And you can see it on the show floor. So 400 gig from a systems vendor's perspective, Dave's going to talk about. 400 gig E in the data center, Brad's going to talk about. And then we'll have some open discussion and questions and answers. So this is the Ethernet speed roadmap from the Ethernet Alliance. So this is readily available on their website. We've happily been going along 10 times increments from the early 1980s until 2010. 2010, when we introduced 100 gig standard, we also introduced 40 gig E. That was the first time we broke from that 10 times step. Why did we do that? Well, simply to connect to servers at a better cost point. So servers knew they were going to need more than 10 gig at that time, but they thought the jump to 100 gig was too much. After that, we started the 400 gig project, and since then, a bunch of other projects have started. Why 400 gig instead of a terabit? Well, simply because the physics are too hard to jump straight to terabit. So that's the story of 400 gig. 200 gig came along recently, and I'll talk more about that. 25 gig and 50 gig are response to server interconnect needs. Well, I just said that 40 gig was for that, but the benefit of 25 gig today's server interconnect is it's a single lane. So it's reusing the server or the SerDes technology to go a single lane to a server to the top of rack switch. 50 gig is going to do that. We're standardizing 50 gig now for a single lane within IEEE, and that'll be a single lane 50 gig top of rack to server kind of connection. The 5 and 2.5 gig are a little bit different. That's kind of an optimization of a cost point to get to wireless access points. So lots of different speeds for lots of different applications. So Ethernet's really spreading around. So a little bit of history of 400 gig E. The first study group meeting was way back in May of 2013. So almost 4 years ago now, quite a long time. And we'll be talking about why that's the case. Dave will expand on that also. First task force meeting was held in May of 2014, so a year after the study group was formed. And it's called 802.3 BS in IEEE speak. The first draft of the standard was the year later in 2015. And we're now on draft 3.1, we're about to come out. So we're in the final ballot cycle for 400 gig E. 200 gig E was added to the project in June of 2016. It reuses the 400 gig architecture, and the logic is in that same task force, and the single mode interfaces are in that same task force. We split up the 200 gig, and the newer multi-mode interfaces and the copper interfaces are in a separate task force called 802.3 CD. So that's also going on in parallel. We're scheduled to release the final spec later this year, at the end of the year, although that possibly could move up a few months if we make good progress on the standard. New technology being developed in the project, 50 gig PAM4 with 50 gigabits per second with PAM4 modulation has been developed in this project, 802.3 BS. So that's 25 gigabaud for both electrical and optical interfaces. And there's one instance of an optical interface that's running at 100 gigabits per lane, I guess it is. And that's 50 gigabaud using PAM4 technology also. So things have gotten harder. I told you why we didn't go to terabit and why we're at 400 gig and below, because things are very hard. We're always in parallel interfaces, both electrical and optical interfaces. Things are tough, so we have now FEC mandatory on all interfaces for 400 and 200 gig. We're using more complex modulation, PAM4. We have higher speed wavelengths, 50 gig or 100 gigabits per second. So that's just very difficult to do, and to get better trade-offs between the logic complexity and the complexity of the optics or the electrical SerDes, we have added FEC to all interfaces. It's an end-to-end FEC, so it goes from one end all the way to the far end. So you can have multiple electrical and optical interfaces covered by that same FEC. So in the IEEE spec itself, we have a budget, right? Electrical interface gets a certain amount of the budget, and the optical interface gets a certain amount of the budget. And the optical interface, turns out, gets most of the budget is what we decided. So the raw BER is around 10 to the minus 4, and that corrects with the Reed-Solomon 544, 514 10-bit symbol FEC to about 10 to the minus 13 BER. Just a little bit about the optical modules. So if you look around the floor, the show floor, you'll see some of these modules around. You'll see CFP8, that's the initial form factor for 400 gig E. That's in a number of the booths, and I'll talk about that demo that's going on in multiple booths at the end of this presentation. It can support a 16 by 25 gig electrical interface to that module, and it can also in the future support 8 by 50 gig PAM4 interface if you want. There's a couple other optical modules that are competing for the next generation or the second generation 400 gig E market. That's the QSFP DD on the left-hand side there and the OSFP. So both of those form factors have 8 SerDes lanes now, so you can interface the 8 by 50 gig electrical PAM4 interface to those to get to 400 gig. So you'll see some instances of those in a few booths, like the EA booth has both mock-ups of the OSFP and the QSFP DD. So there's a couple of module form factors out there, and it'll be interesting to see how that plays out in the industry. This is a slide about 400 gig versus 200 gig E. This is one company's view. So Light Counting let me show this slide. This is what they think the mix from a revenue point of view between 400 gig E and 200 gig E will be. This is just their opinion, right? So it'll be interesting to see how that plays out. Brad will talk a little bit about how he thinks 400 gig will be useful in the data center. So we'll hear from him on that. But this is one possibility. I think what will happen is the per bit module cost will drive the market. So if 200 gig is on a per bit basis is cheaper than 400 gig, then you'll see that win for a while until 400 gig catches up with that. So it'll be interesting to see what happens in the market for these two speeds. And that's my last slide, so I'll turn it over to Brad now. Sorry. No, that's
okay. Welcome, everybody. My name is Brad Booth. I work for Microsoft in our Azure networking team. And I thought I'd come in and talk a little bit about, because everyone asks, well, you know, what do you guys want for the next speed? Are you guys going to use 400 gig? Yes, we will. We've been actually very supportive of the work going on with 400 gig, only because, frankly, everyone in the world is moving to the cloud. Whether it be ours or whether it be someone else's, there has been a massive demand, bandwidth demand, storage demand being placed on the cloud network. And so what does this typically look like? This is sort of what we expect our architecture will look in about the 2019 plus type of time frame. Now, if you notice, I've got what I call an RNG there in the tier 3, and I'll kind of explain that a little bit more. But in about 2019 beyond, for that generation, what we call the 400 gig generation, the server uplinks are predominantly going to be 100 gig. That we can do today with 100 gig DAC cables. So we know that that technology already exists. It exists in QSFP28. It exists in micro QSFP. We have access to that market, and I expect that to persist through 2019. What I expect beyond that then is this to become a 400 gig market. And from the tier 0 to the tier 1 will be, in our case, that's a row. So tier 1 is our row architecture. That's an AOC. This has to be the lowest cost, because when we do a data center build, we rip and replace. We don't do a pay-as-you-grow strategy. We do a rip and replace. So that technology gets forklift brought in, dropped in, it sits there for 3 to 4 years, ends of life, haul the whole row out, and put a new row in. So above that, from the tier 1 up to the tier 2, we predominantly use parallel single mode fiber. Why do we use parallel single mode fiber and not duplex? It's because we built the fiber as part of the infrastructure of the building. So at some point in time, if a CWDM module comes in that's cheaper than a PSM4 module, we would gladly use it, because now we're driven by the cost of the optics. So we looked at PSM4. We were very much an advocate inside the IEEE for 400 gig, 400 G-based DR4. That is our 500 meter reach kind of concept that we play with. From the tier 2 to the tier 3, if it's within the same campus environment, it could either be a DR4, it could be, hopefully, it won't be an FR8, but it might be, there's a lot of talk about doing an FR4. Or in these other cases, how many people have not heard about what we're doing with regional gateways? Yeah, okay. It's okay to admit. I mean, this is a new concept that we're moving to. So we used to build, this RNG used to be built in concept on a campus. So a campus is about 2 kilometers by 2 kilometers. It's, a data center building's about the size of one of this, and we'd have 4 data center buildings on a campus. What we realized is that for us to deploy and be able to build to meet the demand of, people wanting to move to the cloud and the internet and everything else, we needed to be able to build these faster. So when you're building a facility like this that's 128 megawatts, it's really hard to procure enough land, enough power, enough infrastructure to make that happen at a growth curve that matches how we have to build these. So for us to be able to do this at 400 gig, our push was that we need to be able to change this architecture. So now we build these colos that are separated by about 70, 80 kilometers, and those uplinks between the tier 2 and tier 3 are either 400 gig DR4 if it's on the same campus, or this 400 gig ZR project that the OIF just started recently to be able to allow us to do up to 80 kilometers. So if you're inside the colo, like I said, it's 2.5 meter DAC maximum. Probably for us at 100 gig, it might even be less than that. We're actually depopulating the racks of servers only because we start running out of power in the footprint. AOCs are the next hop, and then we've got our 2 kilometer, we call it less than 2 kilometer optics. It's not a reach dependent number, it's actually a loss dependent number. So typically we can use DR4 because we fit within that 3 dB loss number within those links. We do have the occasional exception where we have an older facility. We've been building data centers longer than anybody out there. So we do have some legacy equipment out there where the fiber's a little older. It's got maybe a few more splices or patches than we like. So we use an FR4 potentially in that. And then we use the ZR for the uplinks. And that is just mated directly to what is our regional network gateway that does all our long haul transmission, as well as collectively bringing all these colos together in an area. So we deploy more than one gateway, redundancy. So we put multiple gateways in. They connect to all our colos that we have within that region. We bring the DR4 if it's on a campus, or the ZR into that. And when we go long haul, those long haul links are coherent links. And we expect that in this time frame, when we're doing 400 gig, we've got 400 gig that leaves the tier 1 all the way out to our long haul links being able to support 400 gig. Thank you.
Okay, hi, I'm Dave Bofelt. I'll talk about basically 400 gig from a system vendor's perspective, and I'm going to talk a little bit about the industry, sort of reflection on how it's changed during the time 400 gig is going on, a little bit about 400 gig project itself, and then some about the sort of good side effects of having something like 400 gig. So one of the interesting things, if you look at when we started 400 gig, and the time before that, the world was, for new speeds in Ethernet, was structured so that the system vendors would work with the end users, and here the end users of the telecoms, to define new rates and the new features and the new PMDs and everything. And then the telecoms would gradually deploy that new technology, it'd ramp up, it'd finally become cheaper and cheaper over time, and then it'd start getting adopted in the rest of the industry. So enterprise data center and the classic things like that. As a system vendor, we have to support all the things. Anything that anybody thinks about, we got to be able to plug in. And therefore, we tend to be the folks who act as a glue between all of the different vendors. And so you have the optical vendors and the copper vendors and all this. We sort of help negotiate and make sure that the end users and needs are met in a balanced way, and the pain is evenly spread across everybody. You can't just nail one of the media types and let all of the other ones suffer. You need to sort of make sure all of them can be successful. And this is what we started 400 gig. Now, I think 4 or 5 years later, depending on when you really consider us kicking this thing off, things have actually changed dramatically. Now the hyperscale folks are driving the new technology discussion, and the carriers are really following a lot more. They've sort of stepped in the background and letting the hyperscale guys move things forward. And one of the interesting things about this is the hyperscale folks are also system vendors. They're building a lot of custom equipment. Not all of them, but some of them are. And so you have them out talking to the vendors as well as the classic system vendors talking to the vendors. And our needs are not necessarily exactly aligned because a lot of the hyperscale folks are building proprietary building scale computers where the rest of us are building more commodity stuff. And the other interesting thing they do is they really want to deploy new technology at scale as soon as it's available. My boss is out there. And so all of a sudden, instead of this slow ramp, they want to be able to buy huge numbers of stuff, and then that may be the only order they do and move on. And so as an industry, it's kind of hard to maybe deal with that initial volume. The other thing that's happening is in IEEE, we do define PMDs, but one of the most important things we do is define a PCS architecture and a electrical architecture. So we end up making what is sort of a universal slot on the front of the computer, in the front of the router. So say it's a 400 gig E slot, and other people will build stuff that fits into that. And so IEEE produces a bunch of compelling PMDs, but also the MSAs are producing a bunch of compelling PMDs. If you look at 100 gig E right now, there's a huge collection of available modules out there, and this is actually a very good thing. But it also means that when we're defining the architecture for this stuff, and we did this very much for 400 gig, we need to think about all of the stuff that may happen in industry, not just the stuff we're currently building, and that's an interesting trade-off. So it's been observed that 400 gig has actually taken a while to finish as a standard. It's sort of locked and loaded now. I think we're in the end days, and we'll be done by the end of the year. And there's real 400 gig E hardware in the rooms today, which is really very exciting. One of the reasons it took so long is we actually had quite a few distractions, and Mark talked about this some. We backfilled 25 gig, 50 gig, third generation 100 gig, and this new 200 gig E thing. And all of this happened after we started 400 gig. And if you look at like 25 gig and 50 gig, they're both heavily oriented towards servers, which means the volumes are higher and people get very excited about them. And so that's sort of, there's only one group of people in the world that actually build all of this stuff. And so we have to balance our effort across all of them. And so that sort of slowed some stuff down. And it was very weird to backfill all these rates. That had never really happened before. And it makes sense in hindsight because now we have this nice collection of Ethernet rates to support a market that's much, much, much richer than Ethernet used to be. But it was a new thing. The other thing we did is new technology development, really significant stuff. 50 gigabits per second, 100 gigabits per second optical, 50 gigabits per second electrical. And these are useful as a communication, as standard PMDs. But things like 50 gig electrical are also very useful for a system vendor because we use that inside the box to make sure we can glue all the boards together. And we may not use it as standard Ethernet, but we're using exactly the same technology, and that's a very key thing that comes out of the standard. And finally, 400 gig is driving density. And so Mark showed the new module types that are available. You need to have a module that can take in 400 gigabits per second. Well, one of the other things you can do with that, besides providing 400 gig E, is you can provide two 200 gig E's and four 100 gig E's. And this very much is going to enable the next two generations of roadmap for dense 100 gig. And since 100 gig is headed towards commodity right now, this is where I think, my prediction is this is where the majority of the market, the majority of the systems sold, the majority of the modules sold will be for dense 100 gig. It enables 400 gig, and a lot of people will be using that in some volume, but the faceplate density really is a key thing. And then Brad brought it up, but there's this other thing, this onboard optics. What happens when you no longer can actually make the modules denser? We're right at the hairy edge of that, possibly. And so Kobo will then provide a new set of tools for making things denser once the faceplate no longer can scale. And the timing of that and exactly the shape of that is what I think a lot of the system vendors are working on right now, and it'll be interesting to see how that evolves. So back to Mark.
Okay, just, oops. I thought there was one more slide. Oh, there we go. Okay, so I just wanted to briefly talk about the demo that's going on the floor here. So it's a multi-booth demo, so relatively unique. At the center is the Ethernet Alliance booth, which is right over there. So there's 4 boxes in the Ethernet Alliance booth, which are running 400 gig E, and then they connect to 4 other booths. So you see the booths up there, the Xilinx, Broadcom, Finisar, and Viavi booths. So you can go check out the 400 gig E demo at any of those places. It's real multi-vendor interoperability at 400 gig E. So to me, that's showing that the standard is very mature at this point, and vendors can go off and implement it and talk to each other without a problem. So go check that out. Now we're going to go to questions. Any questions out there? Please step up to the mic if you have a question. I'll start by asking the first question. So Brad and Dave, so we talked about 400 gig and all the other speeds. I wanted to get your opinion. I know we're just starting the conversation at IEEE, but what's next? What's the next speed? And why?
So I think I've got a record last week of saying this, that I am less concerned about the next rate. What I am concerned about is the next Ethernet rate. What I am concerned about the next SerDes rate. And so we've just started the discussion about whether 100 gig SerDes are going to happen. If they do happen, how far can they go? What are the system implications of that? Is it just a science project that technically it works, but I actually can't ship a practical system with it? And what that's going to do is that gets back to the module discussion is, can we actually scale the faceplate one more generation? And if we can, great. We can keep building the systems the way we've been building them. It looks like we can build the ASICs for one more generation at least. We can keep building the way we've been building it. Customers see the system the way they've been seeing it, and that's fabulous. If that doesn't work, we need to change how we build systems, whether it is something like Kobo or whether it is a different form factor, a different way of gluing the system together. We've got to figure that out, and that's actually going to be a very interesting change. And so I think I look at, what's the next rate? Let's focus on the SerDes. Once we can build a QSFP DD that takes 800 gigabits per second, then it'd be very straightforward to build 800 gig E. And so that would probably be the next rate. When we actually start 800 gig E, I'm less concerned about.
Brad?
I guess I would say my prediction is actually the next speed is driven very much by the SerDes technology. My perception is that it's not 800, it's 1.6. The reason for that is that 800 is not, conceptually you could do 800 today. The Optical Modules support 16 by 50 gig interface, so conceptually you can build an 800 gig module, but that today would just be 2 400s. It's not that complex for the industry to do 2 by 400. You can bring other technologies to bear, and it kind of says, okay, well, do I spend a lot of time in IEEE to do 800 gig when it's really 2 by 400 is almost the same thing. Yeah, we did a 200 gig Ethernet, but talk to the number of people that plan to use 200 gig Ethernet and you'll find the numbers 1. But with 1.6, I think it says, let's wait for the technology to be available in SerDes. We do have the capability. We have a 16-lane interface module that's been developed or in development. We will have all the other necessary tools there. Then we can bring a 1.6 to bear. Let's let the market get an ROI on that 400 gig before we cut it too short.
Yeah, go ahead.
Can I ask a question?
Yeah.
I want to ask a question. So when you say not 800 but 1.6, is that you don't care about a MAC rate of 800 gig, you're perfectly fine waiting for that, or are you assuming that we're going to do something like 2 by 400 with Flex-E that gives you a MAC to MAC rate of 800, and we don't have to bother defining a new PCS until then?
Yeah, so you can actually effectively do a lag or a Flex-E very effectively with 2 ports. It's actually not that too inefficient. Where you get inefficient is when you get to 4. And that's why the pain point for a lot of these guys, if you want to try to go up in scale. So for example, if you wanted to take 4 100s and do 400 gig today, if you used a lag protocol on that, the inefficiency of that starts to kick in, and it's not, you don't get 400 gig worth of bandwidth. So it's nice to have that 400 gig Mac. That's why to me, 800, I'm probably going to do it as 2 400s. I will have an 800 gig module, but behind that will be 2 400 gig Macs. The next time that gets interesting from a Mac rate, because that Mac rate affects the rest of my switching protocol. What we do at the physical layer is not as nearly important as what we would like to believe it is what happens at the higher layer protocols, because that is all the routing protocols, the size of the tables, everything else that affects this. So when we make that move, it needs to be at a large enough increment that people are willing to make that investment to build those pieces of equipment.
Okay, so 800 is just not enough of a jump. You want at least 4 times jumps to make it worthwhile to upgrade your data center.
Yeah, I can build modules underneath that at any data rates and support, lower Mac rates with higher bandwidth modules to get density. But when it comes to the Mac rate, I like that 4x pop.
Okay, thank you. Any questions from the audience at this point? Okay, seeing none, then I'll ask another question. So, I think
You got to go to the mic if you got a question.
Yeah. If you have a question, please go to the
I
mic.
see a finger up, but did you want to? Oh, I see. This point.
So my next question, follow on to that, is kind of about optics, right? I know you led a panel on COBO this morning. COBO is a coalition for onboard optics. It standardizes onboard optics so you can solder them directly down to the board. But you also said for 1.6 terabits, we have a module, we have a CFP8, which has 16 lanes. Where do you think the cutoff port, or who will use what and why? I mean, COBO versus a pluggable.
COBO versus a pluggable. Well, we officially went out with an RFI on COBO. So we do have plans to use it only because when we looked at the faceplate density, so if you start looking at what it takes to build these switches and these systems, right? How many people worked on building systems that did 25 gig NRZ signaling to the optics? Few, yeah. How easy was it? So we're going to go to 50 gig PAM4 with the same length of electrical trace and a 9 dB hit because we went to PAM4. This is going to get ugly. This is going to get really ugly, especially if you look at how I get to 800 in a module, or whether that be a pluggable or whether that be a COBO. You realize when we start looking at this, that reach, that performance of that reach, and you're making 30s, and we've had some guys do some incredible SI work for COBO, and the experience was just changing that reach, even by 2 to 3 dB, the impact on being able to build these systems went up significantly. The other aspect is that a lot of us are still forgetting is that we keep talking about these modules on the faceplate and the power that they're capable of, right? QSFP-DD, up to 12 watts. OSFP, up to 15 watts. COBO, we don't even know what the power limit is. It's far beyond what those two are capable of. CFP8, I think it has, 25 or something. So when we start looking at that, and you talk about plugging that into a faceplate, the one thing that everyone tells me on the floor, and I don't build lasers, but everyone tells me lasers do not like heat. So if I'm going to be sticking something that's 12, 15, 25 watts into a 32 port faceplate and try to suck air through that in a 1 RU, my bet is we're going to see a lot more reliability issues in those optics. By changing the thermal footprint, which is what an onboard does, we change the potential reliabilities. So that's why we believe it's going to be a natural progression. I don't know anyone in here that's telling me they can do 1.6 terabit in a pluggable today.
Yeah, you'd need. Yeah, I think. I won't argue with that. I think there's going to be a pressure in the industry to keep the status quo going as long as we can.
Yep.
And I think things will fall off the end if they don't fit. 400G ZR coherent in a little tiny module. Maybe, maybe not. We'll see. Kobo definitely is easier. Will we be able to go beyond an 800 gigabit per second module? You know, if we take the two QSPDD and OSFP, they have 8 lanes. Are we going to get 200 gigabit per second SerDes in there? Maybe. I didn't think 100 gigabit per second SerDes were going to work, but now we're talking about them with straight face. So I think there's we may have one more generation, then we got to look at the stuff. But then we're also going to have to figure out the implications of the onboard optics, and that either you have homogeneous, you get shipped the router with all the optics configured when you get it, or you've got to pull a board and actually take the optics off, which probably means bringing the whole thing down. And so you no longer have, hitless reconfiguration of the media type. And can we deal with that as an industry? Yeah. Is it going to be different than we're doing now? Yeah. And so it's going to take a while to learn which the best end goal is. So.
And to touch on that, I think one of the things that we realized is I'd rather learn that now when I've got a backup plan. If someone, we built these systems and we realized, okay, Kobo was extremely painful. We'll wait till we're absolutely driven to have to use it, but we're not going to know that. We might as well learn while there's still a backup. We've done some basic analysis. We feel very comfortable because we don't do a build as you grow. We buy the things, we know exactly what those ports are. They're stamped. We buy hundreds of those switches that are stamped exactly same way, with all the same optics deployed, and then we roll them out and deploy them. So to us, wrapping that little board with metal in a metal cage, it's not a big win.
Okay. We're getting the signal. We're out of time, so I'd like to thank again my two panelists, Dave and Brad, and thank you for listening. Have a good show.